Okay, I didn't get a chance to finish the last problem. I want to do that on the last video, but I'm limited to 15 minutes, give or take. So the last problem, integrate g of x, y, z. Again, the surface integral of this function, well, that's the 3D over the portion of the plane x plus y equal 1, and that's right there. Running from the first octant from z equals 0 to z equal 1. So I want the double integral over s of g of x, y, z in this case, right? D rho, that's going to be the double integral, and that's going to be, let's see how that works. X, now I have to make a choice. When I look at this, I could say y equal 1 minus x. That's the norm. If that's the case, then when I get here, I'm going to write 1 minus x minus z. So this is running in terms of, if I'm looking at this, from the y perspective, I'm seeing x and z, and I see 0 to 1. So I'm seeing pretty much this portion. And in this case, I'm going to run, I could say that x run from 0 to 1 and z run from 0 to 1. It doesn't really matter here, right? But what's missing is one more piece, and what is that? And that would be, in this case, the square root of, and let's see how this works. If I'm solving for y, it's going to be y sub x plus 1 plus 0 squared, right? Because now this is going to be placing that one squared, right? So here I altered the problem, and there it is. From here on, it's nothing more than 2x minus z plus 1 times the square root of 2 dz dx, and we could continue this and wrap it up, right? So again, if I have y as a function of x and z, then the gradient would be, if I get everything on one side, 0 on the other side, the gradient would be f sub x squared plus 1 squared plus f sub z squared. And you could alter that accordingly. Okay, we have another theorem. It says, given a vector field, three-dimensional with continuous components and smooth surface, directed field, with us having chose a field of normal unit vector and orientation on S. In this case, what you're talking about, this has, or actually, let's make it circular a bit. So here, elaborate on what that means in a minute. There. So let F be a vector field in three-dimensional space with continuous components defined over a smooth surface S having a chosen field of normal vector. Then the surface integral of F over S is given by the following. I'll elaborate on what that means in a minute. This integral is called the flux of the vector field the vector field F across this surface S. And all what they did, they added this component, and we have two ways of really figuring that out. We could say that's F. If I'm talking about a unit normal and I'm given R of u and v, well, a normal to the actual surface would be r sub u crossed with r sub v divided by unit magnitude of r of u crossed with r sub v. And we know what this is, right? Isn't this right here? R sub u crossed with r sub v du dv, and that's what we're left with. Or I could say this is the double integral over region S of f dotted with, and if I'm given z equal some function of x and y, the catch is I need to make z minus g of x, y equals 0. Call this f, and here I will take the gradient of f divided by the magnitude of the gradient of f. And if you recall, if we're given z as a function of x, isn't that the square root of f sub x squared plus f sub y squared plus 1, which is the magnitude of the gradient, right? dx dy, depending on how you're looking at that. And there it is, and that's how it works. And again, you could modify those accordingly depending on what you chose there, and I'll point that out as we do a couple of problems. This book only refers to this. They really do not use this at all. We could use it. That's one example of what you're finding. Depending on the vector field, and you have this surface, right? If you could find those unit normals, you could figure out how much flux is coming out of that. And remember, those are all perpendicular, depending on the angle and all of that stuff. I'm going to put that on the side. You could view it later. For now, let me do some problem. So on number 20, here's a vector field. Out. Oh wait, it went away. Okay. Sorry, I had a sneeze and it went away. There's the vector field. We were saying outwards, normal away from the YZ plane. YZ plane, not something you have to concern with that much. There is Z and there is Y. So outwards, normal away from, so it could be in this direction or this direction through the surface cut by the paraboloid. When you look at y equal x squared, you will figure that out. So x is between -1 and 1, and by the plane z equals 0 and z equal 2. So y equal x squared. Again, the graph is not a must. We don't need the graph for this. Between 0, x equal -1, and x equal 1, right? That portion, right? Something like that. Yeah. And if y equal 1, that if x equal -1 or 1, then y is cut off by 1 as well. Now, if I want to do the way the book does it, they say, well, let's describe this with a vector, since they only describe this with a vector, and let's see how it works. They look at what's given. They say, look, if we let this be x, then y equal x squared minus 1. Very good. And then z. Now we got it in terms of two unknowns, and that's always the catch. We want z to run between 0 and 2. That's easy. That's given. And we want x to run between -1 and 1, and that's simple. And now all what we have to do is find r sub x. So basically, this is where they're going for. They're going to say the double integral of f dot n ds is going to equal the double integral. In this case, they're going to take f. F is x squared. Nope. F is 0. X squared -xz. That's fine. If there was anything else, I would have replaced it. Dot it with, and what did we say it was? r sub u crossed with r sub v. In this case, what is r sub x? R sub x is actually 1, 2x, and a 0. R sub y is r sub z. So stuck on x and y. That is 0, 0, 1. And if I take r sub x crossed with r sub z, I'll get a vector. And what is that vector? That is 2x, that is -1, and that is a 0. So if I dot this with 2x, -1, and a 0, and I run dx dz, let z run from 0 to 2, and x from -1 to 1, that would be the quantity 0 minus x squared plus 0 dx dz, and there it is, you're done. And if you work this out, you should get, I think, a 4/3. I do want to point out that you have another option. This book only uses this. And there's a price for that. I'll show you what that is. I could here say, you know what? There's the function. There's the limiting factor. It is y equal x squared. So I could say 0 equal x squared minus y, or the other way around. And I could say, let this be f, and I'll take the gradient of f. Man, that'll do it. What's the gradient of this f? Partial with respect to x, partial with respect to y, and a 0. And do you notice that this right here and this right here are identical? And do you see how quickly I was able to get there? And I could do the same dx dz, and I could run from 0 to 2 and -1 to 1. And number 26. So you'll figure this out. This is the vector field. That's not a problem. Don't worry about that. Outwards, normal away from the z-axis, and with a cone, you notice whenever they're dealing with a circular part or a cone running from 0. So if I put 0, I'll get the origin. Right? That means they're both 0. And if I put a 2, I'll get 1 equal the square root of x squared plus y squared. That means that's r equal. So I could say let r of u and v equal u the cosine of v, u the sine of v, and z will equal twice, kind of like r cosine theta or sin theta. Isn't that twice r, which is in our case u? And we could let u vary between 0 and 1, and the angle vary between 0 and 2 pi, because when I look at this, the only thing I see in 2 dimensions would be the circle. The reason I wouldn't go for z minus twice the square root of x squared plus y squared and find the gradient of that, I'll have a hard time finding the limits on x and y. If I want to write a double integral of this g function times the gradient of f, I'll have a hard time figuring out what those limits are. Versus here, I know the limits already. I know the limit is 0 to 2 pi. The limit is 0 to 1 of f. What is f? I'm sorry, the other piece. That's going to be u sine of v squared, x times z, u cosine of v. Z is 2u, and -1. Dot it with, and now I have to find that vector, and that's pretty much the problem. That is, what is r sub u? That is cosine of v, sine of v, and a 2. What is r sub v? That is negative u sine of v, u cosine of v, and a 0. And you find r sub u crossed with r sub v, that vector right there, and that's the vector you're gonna put right there. And that turns out to be, let me see if I can do it quickly, sine of v. And if I put, no, the I messed up. Oh boy. Okay, well, you just put it there and you go from there. I'm running out of time. And there's the homework.